This is called permutations and combinations and the binomial theorem, and I've put the binomial theorem in brackets because although it is connected specifically to combinations, the binomial theorem is worlds apart in terms of what we do with it compared to permutations and combinations. And one of the things that we're going to start off with today is making sure that you understand the difference between a permutation and a combination. And I can tell you right now what the difference is. A combination is a selection of items from a group. So if I said that I'm going to take 5 of you out for ice cream, I'm talking about combinations of people. These 5 or these 5 or those 5. So it's just a selection of items. A permutation, on the other hand, is a selection of items in which an order is important, in which each individual selected is different in some way than the other individuals. For example, I have 5 gift cards. I have a Boston Pizza gift card, a Tim Hortons gift card, a Subway gift card, an Earl's, is Earl's still around? An Earl's gift card, and a Coliseum Pizza gift card. And I'm going to pick 5 people to give those gift cards to. So if Allie gets the Boston Pizza gift card, that's different than if Allie were to get the Coliseum Pizza gift card. And what we would say in that situation is order is important. The order in which I hand out the cards is important. So things like phone numbers are permutations. Things like the combination lock pattern that you use, the combination that you use to open your lock, is not actually a combination, it's a permutation. On the other hand, if I'm playing poker, that's a combination. Because, I mean, if I get 10, Jack, Queen, King, Ace, all of spades, I don't care the order in which they were dealt to me. I have a royal flush. Okay. We're going to start off today by looking at something called the fundamental counting principle, and you should be aware that even though, and this I don't think the textbook makes it perfectly clear, even though the fundamental counting principle is taught in this section in your textbook, which is all about permutations, there are many cases where we use the fundamental counting principle for combinations. In fact, a lot of the examples in this section are actually combinations, but you're just not officially taught what combinations are yet. So we're going to start off with a very basic problem to introduce us to what the fundamental counting principle is. Yeah, how many different styling outfits does he actually have available to him when he goes out on the town on his vacation in Maui or wherever? So there's Bobbie Bear, and there's 3 pairs of pants. And there's a condition here, unless Bobbie Bear wants to get arrested, he has to be wearing pants and a shirt, okay? So this is not a difficult problem, and this problem is pulled directly from an elementary mathematics lesson to teach students at a very low mathematical level the idea of counting. And the idea is that if one morning Bobbie Bear gets up, and clearly you're not going to draw all of these, Bobbie Bear gets up one morning and he wears a yellow shirt, he can put on a red pair of pants. So he can wear that combination, and it is a combination. Bobbie Bear gets up the next morning and he says, you know, I really like that yellow shirt, but I want a different outfit, so I'm going to put on the blue pair of pants. I think you see where this is going. He gets up the next morning, he looks at the yellow shirt. He's got pizza sauce all over it. Even though it's got pizza sauce, he still wants to wear it. So there's 3 different outfits he can wear with the yellow shirt. If we take a look at now, the next day he gets up, he's going to wear the green shirt. Well, he can wear the green shirt with the red pants. Or the following day, he can wear the green shirt with the blue pants. Or he can wear the green shirt with the orange pants. And I think with a little bit of thought, this is not a difficult problem. You know, for an elementary school student, for a grade 3 or 4 student, it might require more thinking. But I think you see that we've exhausted all of the possibilities here, haven't we? There's no other different outfits he can wear. So the answer to the question is 6. And by the way, you are not going to be solving these problems in that fashion. You were asked to list all of the different outfits, so how do you do that without drawing them? Well, we can use an ordered pair. We can say that this is X and this is Y. We can say the shirt color represents X and the pants represents Y. So if we wanted to list them all, our list would be YR, YB, YO. So I'm writing the letter of the color of the shirt followed by the letter of the color of the pants. And then we could have as well GR, GB, and GO. You get my drift here? Do you see how I'm representing these as an ordered pair? Okay. I mean, you could just write them out in words as well. Let's try another one. At an ice cream shop, there are two different types of cones, regular cone and a waffle cone. There are 3 different flavors of ice cream. So this is just some little cart that's at a beach somewhere or at a park. Okay, they don't have a lot of stock. What kind of ice cream do you have? Oh, we only have strawberry, vanilla, and pistachio. And we also have sprinkles, and you need to have sprinkles. That's the condition here. Okay? You say to the vendor, you go, no, I don't want sprinkles. They say, go away. You have to have a cone, you have to have ice cream, you have to have sprinkles. I'll talk in a second about what happens if you have an option of having sprinkles or not. So a single ice cream dessert consists of choosing a cone, choosing a flavor of ice cream, and choosing sprinkles. How many different ice cream treats can you buy? Well, this is complicated. If we started to draw this or write it out, we would have to say, well, you can have a regular cone with strawberry and chocolate sprinkles, or you can have a regular cone with strawberry ice cream and mint sprinkles, and we could try to organize it that way. But we're going to draw what's called a tree diagram. And you don't have a lot of room here, but you want to space things out because this diagram is going to grow width-wise in a second. The R stands for a regular cone and the W stands for a waffle cone. These are your 2 options to begin with, your 2 choices. Not 2 choices, your 1 choice with 2 options. And if you choose on one particular day that you want to get a regular cone, you have another choice to make. You can choose to put strawberry ice cream in that regular cone, vanilla ice cream in that regular cone, or pistachio ice cream in that regular cone. But don't forget, you could choose a waffle cone instead. And if you chose a waffle cone, you have those 3 options there. And right now I want to impress on you the fact that there are 6 options staring you in the face. 6 options. Regular with strawberry, regular with vanilla, regular with pistachio, waffle strawberry, waffle vanilla, waffle pistachio. But now let's say that you go with the regular cone with strawberry ice cream. Well, you can either choose chocolate sprinkles or mint sprinkles. You don't need to indicate this, but this is one choice. This is a different choice, right? Every path from the top of your tree diagram down to the bottom is an option. Clearly, if you choose the regular cone with the vanilla ice cream, again, you have 2 choices of the type of sprinkle, and it continues. So really, if I said to you, how many different ice cream treats are possible with a regular cone? It's 6. Because there are 6 items in the bottom level here, that means we have 6 paths to follow. RSC, RSM, RVC, RVM, RPC, RPM. But that's going to be replicated over here. And when we count these out, this is why it's going to be called the fundamental counting principle, there are 12 different treats. Now, I want to just take a break here, and maybe next time I do this unit I'll add this as a secondary question. What if you didn't have to have sprinkles? What if the vendor wasn't that kind of guy that's so down the line? No sprinkles? Okay, that's fine. But you do need a cone and you do need ice cream, right? They're not going to just give you a cone and sprinkle something over it. You need ice cream in the cone. What would the answer to the question be? Well, what would happen is for each of these flavors, you would have an option of no sprinkles. So you could have regular strawberry chocolate, regular strawberry mint, or regular strawberry nothing. And what that would do is increase this number to 9 under the regular, and you would also have 9 under the waffle. Okay? And one more that we're going to do with the tree diagram. Small rental car company. Bobbie Bear goes to the rental car company in Maui. Says, what do you have? They have 3 models, minivan, compact car, and a hybrid. What colors do you have? Black, red, and pink. And they have standard or automatic transmission. And they have enough stock to accommodate anybody's choices. Okay, you can pick any set of options in terms of model, color, and transmission. How many different vehicles could you rent? Well, we have to start off by picking one of these properties of the vehicle. I'm going to pick the model, and I'm going to say minivan, compact, hybrid. I hope everybody can appreciate doing this tree diagram is getting a little out of hand, isn't it? Like it's going to, if I said 12 cars, 12 models, and 18 colors, imagine trying to do a tree diagram like that. It would be torture. But if you choose a minivan, you can go with black, red, or pink. And you're going to have to spread this out in anticipation that each of these is now going to branch off again. If you choose a compact car, you can choose black, red, or pink. And if you choose a hybrid, you can choose black, red, or pink. Now, if you choose a minivan that's black, you can then go with a standard or automatic transmission. And if you choose a minivan that's red, same thing, standard or automatic. Minivan in pink, I think you're getting the idea. Each of these endpoints that is a path with a model and a color is going to branch off into 2 options, standard and automatic. So you get this for the compact and you get that for the hybrid. And the question now is, how many options are there? We don't need to do this. You don't need to go, oh, that's one option. That's one option. I mean, if you want to do that, that's fine, but I'm going to run out of different colors here. You can recognize that you're just going to count how many items there are in the bottom level. And I believe there's 18. Correct? Okay. So we don't want to do it this way. There's got to be a simpler way. And the simpler way is to use what's called the fundamental counting principle. The fundamental counting principle says when you have a job to do, whether it's rent a vehicle, pick an item from a menu at an ice cream stand, or pick a pair of pants and a shirt to wear for the day. When you have a job to do and there's multiple choices or stages within that job, then to find out the number of ways to do the job, you multiply the number of ways to do each stage. So if there are A ways of doing the first stage, B ways of doing the second stage, C ways of doing the third stage, and it continues, then the number of ways you can complete the entire job is by multiplying those numbers together. So if we go back and look at, well, I guess I should talk about this first. This is not in your notes, but I want to introduce this now. It will be in your notes later. The word "and" in English translates to the word multiplication in math. So when you have to do one thing and another, you multiply them together. You have to complete task A and task B and task C. So if we go with that as being kind of a translation of the fundamental counting principle, it's going to make our job a lot easier later. And I will tell you later that the word "or" means plus. If we go back and look at Bobbie Bear's conundrum, bless you, if we go back and look at Bobbie Bear's problem, how many outfits can he wear? Well, he has to put on a pair of pants and put on a shirt. So we take the number of pairs of pants and we multiply by the number of shirts, and we get 6. We didn't need to draw it. We didn't need to reason it out. Cones, flavors, and sprinkles. Well, there were 2 cones, there were 3 flavors, and there were 2 sprinkles. If we multiply that, we get 12. If you had an option of no sprinkles, then the number of different choices you could make would be 3 here. Chocolate, mint, or nothing. And that would change the outcome. When you look at the car problem, there are 3 models, 3 colors, 2 types of transmission. You need to choose a model and a color and a transmission, so you multiply them together and get 18. And this lesson now is consisting of just boatloads of examples where we apply the fundamental counting principle. And as many examples as I can show you in this lesson or this unit, there are many that I can't show you. I can't show you them all. There's just gajillions of different applications of this. Let's take a look at example 1. How many different arrangements of all of the letters of the word reason are there if the arrangement must start with S? So first of all, there are 1, 2, 3, 4, 5, 6 things we have to arrange, so you should write 6 blanks. Bobbie Bear had 2 stages to his task. He had to choose a pair of pants and a shirt. The ice cream problem, you had 3 different things. You had to choose a cone, choose ice cream, and choose sprinkles. This has 6 choices. You have to choose something to put in the first blank, choose something to put in the second, choose something to put in the third, etc. But there's this condition. The condition is that the first letter must start with an S. And by the way, the word arrangement means you're physically moving stuff around. I don't have a whole bunch of R's and a whole bunch of E's. If I put an R someplace, that's where it is. There's a little rule that I will give you here, and that rule says that this is what's called a condition or a restriction. And a condition or a restriction must be taken care of first. So below this first blank, I'm going to put S, and then underneath all of this, I'm going to put, who cares? It's a free-for-all at that point in time. Any letter can go anywhere after we place that S there. So how many different options do I have for the first blank? Well, I only have 1 tile that says S. And I'm using algebra tiles, so you get the idea that we would be moving these around, which means that this is 1. And I have to put something in the next blank. Well, I have 5 letters left. I've chosen 1, it's the S. I have 5 remaining. And I have to put something in the next blank, but now I'm down to 4 left. And the next one I would be down to 3 and 2. And although it doesn't really matter, and 1. Because really you don't have a choice at the end. You're sitting there looking at 1 blank and 1 tile left. There's no option. And we multiply that together and we get 120, I believe, but I would like you to confirm that. We do. So there are 120 different arrangements that start with the letter S. And this is a very simple application of the fundamental counting principle, but I bet you if I didn't teach you the fundamental counting principle, this would be a 5-10 minute puzzle for some people. Right? It's not a simple approach, or it's not a simple problem. The approach is simple if you know the rule. In a classroom, please don't draw 25 blanks. Okay? In a classroom, there are 25 desks. So I have 25 desks in my class, and I look at my class list at the beginning of the semester, and in period 1, I have 25 students. How many different ways can they be seated? And I want to pause here for a second and tell you that the number of different ways the students can be seated is also the number of different ways that I could put their names in a list. I could number these desks by saying desk 1, desk 2, desk 3, and I could start putting their names in a list. The question is, how many different ways can I arrange 25 items? So how do we approach this? Well, one of the ways to approach it is to let, in our minds, the students decide where to sit. But there's going to be some control here. It's not going to be chaos. People are not allowed to pile on top of each other on the same desk. They come in an orderly fashion. Shannon comes in, she picks a seat, and she sits there. The next person comes in, they pick a seat. So from that standpoint, there are 25 different people that can choose to sit in that place, right? There are 24 different people that can choose to sit in this place. 23, 22, 2, somebody comes in late, sorry, you have to sit in that other spot. I mean, there's a lot of other ways that you could do it. I could say that I'm going to make a class list and I'm going to say who goes at the top of the class list. I have 25 different names I could put there. Who's going to be in the second spot in the class list? I have 24. Do you get the idea here? If you were to write this out on a written response question, I suppose you could do this. I see some of you plugging away on your calculator. I'll save you the heartache there. I've done so already. This is what we need to calculate, and I put it into a calculator and I get 1.55121121,1004 times 10 to the 25, which is a hard number to grapple with. I put this into Excel so I could see all of the place values. By the way, it might be curious that it ends in a whole bunch of zeros, but it really shouldn't be a surprise when you consider that, you know, there's a couple of 10s in here. There's also 2s times 5s in here. You're going to get a whole bunch of 10s at the end. Okay. I wouldn't even begin to know how to pronounce that. I don't know. I'd have to look up. I mean, I know millions, billions, trillions. Beyond that, I don't know. But there's a way to abbreviate this. And it's that. It's not 25. That's not how you think of it. Okay? The exclamation point in math means 25 factorial, and by definition, a factorial means you multiply that number by one less and one less and one less, and you keep going until you get to 1. And you do have a factorial function on your calculator. With a 84, I believe you can go alpha format, or nope, alpha table set, nope, alpha fraction, nope, alpha, I'll find it, there it is, nope.
It's just downward.
One more over?
No, it's in that one just down. It's at the bottom. It's at like 9.
Oh, it is in here, but you gotta,
Mine showed up.
yours showed up? Different formats. Let me get this out of the way first. If you don't want to use the alpha key, you go to math. You scroll over to probability. And there it is. Yours is there?
Yeah.
Yeah. I think it might be because I'm not in the math type or math print mode. Anyway, if you wanted to find out what 25 factorial on your calculator is, you would go 25 and then you would access that. And I'm going to fire up my other mode here and just see if it's there. So it was alpha window?
Yeah.
Okay. So if I go and I just don't like this math print mode normally. And I'm probably never going to access the alpha menus. No, see, I just don't have it on mine. Different operating systems, different calculators will have different options. Okay. Anyway, that's the answer to the question. Let's take a look at another one. If all of the letters of the word diploma are used, then how many different arrangements are possible that begin and end with an I, O, or an A? Well, this must be an I, an O, or an A. This must be an I, an O, or an A. Those are the conditions. Everything else, there's no restrictions here. So what I've got are 1, 2, 3, 4, 5, 6, 7 blanks because I have 7 letters. And again, I am arranging them. So if I end up putting an O in a particular place, I can't put an O in a different place. We do the restrictions first. I'm going to put the number 3 here because I have 3 things in my list that I need to choose one from. What number am I going to put in the final blank? 2. That's right. Because I don't know which of these 3 letters I put in the first blank, but it doesn't matter. I don't need to know, and I can't know. What I do know is that one of the 3 is out of the pool, and now I'm left with 2 in that pool. Now, I'm going to go back to the beginning. We don't have to fill in the remaining blanks in any particular order, but I like to go left to right. Who can tell me what number is going to go in the second blank? It is 5. Because we've filled in 2 of the blanks, we've used 2 of the letters, and we had 7 letters to begin with. I mean, one of those 7 is still an I, an O, or an A, but who cares? We still have, out of the 7, we have 5 left. Okay, we've used 2. So this will be 5, and then 4, and then 3, and then 2, and then 1. And you multiply that out. 720 is what I get. The volleyball team is made up of 8 players. One of the things you will learn in this unit is this particular question, to use it as an example for what I want to explain to you. You will see this question dozens of times, and it will have nothing to do with volleyball players, nothing to do with standing in a line, nothing to do with pictures. I can disguise what the basics of this question are in a number of different ways. I can turn it into students writing an exam. I can turn it into a lot of things. So we have 8 players. They're going to stand in a line for a picture. It's like thinking of blank, 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 blank. Okay? Except we want to find out how many ways to line them up, but Joan and Emily have to stand together. It's a complicated question. Here they are. There are 8 people, right? But we are not going to be arranging 8 items. We are going to be arranging 7. Because Joan and Emily are locked together. They must be together. So what we would do there is we would say there are 1, 2, 3, 4, 5, 6, 7 different items, and we're going to have to, sooner or later, 7 times 6 times 5 times 4 times 3 times 2 times 1. Look, sooner or later, we're just going to say the number of ways to arrange 7 items is 7 factorial, right? But why is 7 factorial, which, by the way, I think is 5,040? Why is 7 factorial not the correct answer to this question?
It could result in them being separated.
Pardon me?
It could result in Emily and Joan being separated.
No, actually, this 7 factorial does not result in any where they're separated because we are treating them as a single item. Of these 5,040 arrangements, Joan and Emily are together in every one. But this is not the answer to the question.
They might be in a different order.
Absolutely. Take a look at this lineup. Take a look at this lineup. Take a look at where Joan and Emily are. It's different. So what you have to do here, Bobbie Bear had to put on a pair of pants and a shirt. What the photographer has to do is arrange these 7 things and arrange Joan and Emily. We have to multiply by 2 factorial, which is 2. So the correct answer here is, how is my math on this? 10,080? There are a whopping 10,080 ways to arrange the girls. What if Janice, Becky, and Sophie must be together? Well, I'm not going to, actually, maybe I do have it here. I do. There they are. And sometimes you might need to actually draw something. It doesn't have to be a great diagram, but draw it because it's sometimes not obvious that the answer is going to be related to 6 factorial when you group 3 of them together out of 8. But when I group 3 together out of 8, I'm left with 6 items. So what I need to do is take 6 factorial, because that's blank, 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 blank for these 6 items, and I need to multiply by the number of ways to arrange these girls within their group. And it's not 3, it's 3 factorial. It's blank, blank, blank with the fundamental counting principle. Let me give you an example now of what you might see on an exam. What you might see on an exam is the number of ways to arrange the girls so that Janice, Becky, and Sophia are together is a factorial, b factorial, and I could ask you what are the values of a and b. Or I could say what is a plus b? 720 times 6, I couldn't tell you. Will, do you have an answer? 4320. 4320? Patty and Alice cannot be together. Listen, if you try to figure this out like it's a puzzle, you'll go insane. Okay? You can't figure it out by putting them in a line. Let's find out how many total arrangements there are. Well, that's easy. That's 8 factorial. Forget about who's standing where. Forget about who's best friends with who. Forget about who hates who. And apparently Patty and Alice can't stand each other. If you put them next to each other, there's going to be trouble. Okay? Doesn't matter. Whatever that is, and I don't care what it is, that's the number of ways that they can be arranged. Let's figure out now the number with Patty and Alice together. I know they're not supposed to be together, and I see that some of you are seeing why we're doing this. The number where Patty and Alice are together, well, I don't feel as though I need to explain this again, is the same as the number of ways in which Joan and Emily were together. It's just a different group of people. It's going to be 7 factorial times 2 factorial. I mean, I suppose we can figure out some numbers here. Eight factorial is 40,320, and then I forget. Oops. And 7 factorial, 2 factorial was 10,080. Okay, so 40320 10080. Who can tell me what we can do to those two numbers to figure out how many different ways we could line them up so Patty and Alice are not together? Miles? Subtract. I mean, they're either together or they're not. I explain this usually by saying, imagine that you just have no life, and I give you 40,320 little index cards, and you write down 40,320 orders. Okay? And you stand in front of a garbage can. The garbage can is on the floor. And if Patty and Alice are together, you throw that one out. If they're not together, you put it on the table, because those are the ones you want to count. Clearly, the ones on the table are going to be equal to the total that you started with, minus whatever you threw out. So, 30,240. All All right, consider the letters of the word English. How many different four-letter arrangements can be formed if letters can be repeated? So if you look up here, everyone, letters can be repeated. Look up here. Whoops. I can do whatever I want here. I can have all H's. I can have one H and the rest N's. It's a total free-for-all. There are no other conditions. So how many options do I have for the first blank? Well, 7. 7 different tiles I can choose. How many for the next?
Also 7.
7. Because I'm allowed to repeat. I'm only making 4-letter arrangements. It doesn't really matter, though. The answer is 7 raised to the 4. What if we can't repeat the letters? So now when I take a look at these tiles, they are individual tiles. I can't clone them. I can't repeat them. So how many different arrangements? Well, there are 7 options for the first, then 6, then 5, then 4, naught times 3 times 2 times 1. 20 times 42 is 840. What if no letters can be repeated and the first letter must be an E? Well, that means we can put below the 4 blanks, must be an E here. And again, who cares? It doesn't matter. I mean, it's not a total free-for-all. We can't use a letter more than once because letters are not allowed to be repeated. So this will be 1 times 6 times 5 times 4, which I believe is 120. Okay, thank you. By the way, I would do this question in an entirely different fashion. If the first letter must be an E, then what I would say is, how many 3-letter arrangements can I make from that? Multiple choice exam has 35 questions, each with 4 choices. We've already done this question. This is identical in nature to a question we just did in the last 5 minutes. And it's the one where we could repeat the letters with the word English. The answer to this question is going to be 4 to the 35. Because question 1 has 4 different options I could make for a correct answer. I could make it so A is correct, B is correct, C is correct, or D is correct. Am I allowed, have you ever written an exam that has the answer to one question being A and the answer to another question being A? Well, of course, you can repeat those choices. So you're going to multiply by 4, and you're going to do this 35 times. Which is 4 to the 35, which is an awfully big number. We won't worry about what it is. Number 7. So you can just set this up by putting 6 blanks, because we're going to need 6 blanks. And by the way, I like this stuff. I think this is kind of a different diversion, certainly away from algebra and graphing and functions and all this other stuff. To me, it's fun. Okay? If it's not fun for you, I get that, but it is kind of a fun diversion in mathematics. Car plates in a certain country consist of a letter other than an I or an O. The reason is this government has decided we can easily confuse I's for 1s and O's for 0s. Followed by 3 digits, but the first of those 3 cannot be 0. And then followed by any 2 letters, but you're not allowed to repeat the letters. So the first one has to be not either of these letters. This has to not be a 0. I'll write the word 0. This is any digit here or here. It doesn't say anything about not being allowed to repeat. So those 3 digits could be 111. Who knows? But the first of those 3 digits in that group cannot be a 0. Then, any letter followed by any letter except that letter. Because those 2 letters cannot be repeated. So if you put a B here, then you cannot put a B in the next one. Once you organize this, it's not difficult. You do need to know, and I've put this at the bottom of the page, you are expected to know that there are 26 letters in the English alphabet. You're not expected to know which ones are vowels and which ones are not. Because that's even ambiguous with the whole and sometimes Y thing. You know what I'm talking about, right? And you, obviously, it's a math class. You're expected to know that in our decimal system we have 10 digits, 0 through 9, or 1 through 9 and 0. So this would be 24. This would be 9. This would be 10 and 10. This is 26. And this is 25. And when you multiply all those together, you get the answer. The answer is the less important part of this. The more important part is filling that information in. 24 times 9 times 100 times 26 times 25 gives me 14,040,000. Consider a 6-digit numeral. A numeral is a group of digits strung together. But I'm making a note here that even though there are 6 digits in 0, 2, 4, 3, 5, 6, that is a 5-digit numeral. A 6-digit numeral never starts with 0, because if it starts with 0, it's not a 6-digit numeral. It's a 5-digit numeral. So right away, if we're looking at how many different numerals we can get, this is not 0. But we're not just asked how many different 6-digit numerals are there. We're asked how many odd 6-digit numerals have no repeating digits. So we can't repeat digits, and it must be an odd numeral. If it's odd, this last digit has to be odd. We need to end in 1, 3, 5, 7, or 9. Okay? So we do our restrictions first. And luckily, there's no conflict between the restriction in the first blank and the restriction in the last. If I said it had to be even, that's tricky. Here, there are 5 options. How many options are there for the first blank? See, let me explain. So first of all, don't confuse this number 5 with 5 items being used. We've put 1 item in the pool. I put 9, except I forgot about this. This first digit cannot be a 0. So of all of these 10 digits, 0 is not available for my choice for the first blank. Why isn't it 9 then? Why is it 8? Exactly. That's the perfect way of putting it. It can't be 0, and I've already used a digit someplace else. So now I'm down to 8. Okay. How many different items are still left available for me to choose from for the next blank? 8, because I've used 2. I've used some odd digit, and I've used some other digit that's remaining in the pool that's not 0, so I have 8 left. And then I'm down to 7 and 6 and 5 and 4. It's not a simple question to wrap your head around. What do we have here? 64 times 42 times the 5, which is 25. 67,200. If, everybody, and I don't want you messing up your work on paper, but if digits could be repeated, this would have been 9, 9, 8, it would have been 9, 10, 10, 10, 10. If digits could be repeated. So, in helping us out with the next problem, I'm telling you that the word and means times, and the word or means add. In your notes, do you have a multiplication symbol right in here? Okay. So let's take a look at the next question. In a math class, we are graphing rational functions that look like that. X minus 9 times x minus 3 over, that's a 9, x minus a times x minus b. And we're allowed to put any digits in for a and b. Any. With a condition. We need to create a rational function that has one whole and one vertical asymptote. So would you agree that if there's a whole, it has to be either at x equals 3 or at x equals 9? Okay. We can have a whole at x equals 3 or a whole at x equals 9. Can I have a whole at both? Why not, Brody?
You only have one, and you need a vertical.
I need a vertical asymptote, right? So one of these factors, whether it's x minus a or x minus b, one of them has to be x minus 3 or could be x minus 9. So if we have a whole at x equals 3, let's just say that the b is a 3. If that's the case, you only have one option for b. Only one. If there's a whole at 3, how many options do we have for a? Is it 9? Because as long as it's not 3, that's okay?
It's 8.
It is 8. Why is that?
It can't be a whole itself.
Right. It can't be 9 because then we would have a second whole, and it can't be 3 because we've already taken that. It has to be other than a 9 or a 3, which leaves 8. Or means plus, and we repeat the process. What if the whole is at 9? Well, there's one option for b. It has to be a 9. And there are 8 options for where the vertical asymptote is. So we get 8 plus 8, which is 16. You can easily psych yourself out here and go, well, what if the a's and the b's are switched? But don't go down that road because the order in which you write the factors doesn't change the graph. Okay. And I believe we have one last question to do. I've got 3 different physics books, whatever they are. I have 4 different chem books, and I have 5 different bio books. I want to put them on a shelf, but because of the weird kind of guy I am, they need to be organized by topic. So I want to arrange the physics books, the chem books, and the bio books on a bookshelf, but the physics books must be together, the chem books must be together, the 5 bio books must be together. How are we going to solve this problem? By the way, this is no different. This is no different than me saying I have 3 disco songs. I have 4 classic rock songs. And I have 5 Viking thrash metal songs. And I'm going to create a playlist of those songs, but I want to keep the genres together. Okay? And that might help you. How many of you have an idea of what we can do here? Kai, what do you think we should do?
5 factorial plus 4 factorial plus 3 factorial.
Turns out not 5 factorial plus 3 factorial plus 4 factorial. And by the way, it's not plus because we have to arrange them and arrange them and arrange them. It's not an or situation. I mean, you're on the right track because I could easily say 3 factorial. I got to arrange the physics books. 4 factorial, and I have to arrange the chem books, and 5 factorial, I have to arrange the bio books, but this will not give me the right answer. What am I missing? What else do I need to do? Bobbie Bear needed to put on a pair of pants and a shirt. We need to arrange each of these categories and do something else.
Which order the categories are in?
We have to arrange the categories themselves. We have to arrange the books within each category, and we need to arrange whether it's physics, then chem, then bio, physics, then bio, then chem, on and on and on. And that's the answer. And I'm again illustrating to you that this question can be about books or about songs or about cars parked in a parking lot. I can make it into just about anything. I could say that I have 3 different cars, 4 different trucks, and 5 different, I don't care, unicycles. How many ways can I line them up so that they are all together within each group? I mean, I could say I have a total of 12 people going to stand in a line, and I have 3 babies, and I have 4 teenagers, and I have 5 adults. How many ways can I line them up for a photograph if the babies are all in a group, the adults are all in a group, and the teenagers are all in a group? It's endless, the variations of this. I could say, well, we'll leave it there. You will discover more and more variations of this kind of thing as you practice these problems. This is a very strange unit, I get it. There's a lot of questions here. And you know at this level I would prefer that you do as much as you can. I understand you can't do everything, but this is a situation where you might want to make sure that you do them all. Because you might run across a problem on an exam that's connected to one of these that is not in your notes. Okay? So get started on that. We still have about 15 minutes here, and I will come around and I will certainly help you out.